All right, welcome back, everyone. Let's go ahead and see another example on creating a confidence interval if the standard deviation is unknown. So if the population standard deviation is unknown. So let's go ahead and take a look at our first example. And let's emphasize that this is the population standard deviation. We already know from earlier lessons that the confidence interval for the mean is going to be between my point estimate, x bar. So that's something computed from my sample. So let me emphasize that by marking it green. So that's just my sample mean. And that's called the point estimate. And then we're going to subtract this quantity t sub alpha over 2 times s over square root of n. And remember that s is, again, from my sample, and is also from my sample. And so what I did is I replaced sigma with s, and that we saw that mandates that we essentially use the t distribution. So we saw that via modeling here, that if you replace sigma with s instead, you get these thicker tails. So because of that, we're going to use the t distribution. So just be aware of that. All right. Now, the formula doesn't really change much. Remember, this was the error bound for the mean. And so you're basically adding and subtracting from that point estimate this error bound. It's pretty simple to do by hand, but we're going to go ahead and focus on using technology for this. If you want, I can show you how to do it. Maybe on this example, but we'll go ahead and use technology. The requirement, oh, by the way, because we're using technology, I'm not going to ask you to compute a lot of this. I'm going to ask you to just verify that the requirements are met. So think of this as a little check in order for you to even get started. You need to ensure that you have a valid random sample. Usually we get that from a simple random sample. We need independence, which means that my sample size, n, has to be less than 5% of the population, so less than 0.05 of capital N. And we saw in the probability chapter that this ensures independence even if you sample without replacement. So there's a slight technicality, but hopefully by now that makes sense. And then finally, the last one, the shape requirement. Either you have a random variable that is already known to be normal, or you have a large enough sample size for the central limit theorem to kick in. So that third one is really so that we can use the central limit theorem. All right, let's go ahead and see our example. So example 4. In a survey, 1,100 Americans were asked how many hours they worked the previous week. The average, and again, this is from that survey, so all of this is from the sample. So it doesn't specify, but it does say that the average here that we found was 43.6 hours with a standard deviation of 15.23. So here they're telling me that x bar is 43.6 and s is 15.23. We also know that we asked 1,100 Americans, so that's my sample size. All right, and those of you that are keeping up with this recognize that we more or less have everything that we needed to use our formula. All right, we have x bar, we have s, and we have n. The only thing missing is t sub alpha. So anyway, for part A, it says determine the point estimate for the population mean number of hours worked last week. So I want to emphasize here that they are asking about a parameter now. They're asking the population mean number of hours worked last week. We can go ahead and say that that's mu, that's the parameter of interest here. What is the true average number of hours worked last week? Now, the previous concept basically said that your sample is a good approximation to that. So that's what we're going to go ahead and say. So the previous section emphasize the idea that my population mean is well approximated by my sample mean. And so because of that, the sample mean is called a point estimate because it gives me a good estimate of what the population value is. So here I'm going to say that mu is equal to 43.6. Notice that before we said that's the sample value. When you set the sample value equal to the population value, that's called estimating. Okay, so here we are estimating. All right, let's continue. Are the requirements met to find the confidence interval? And those were those three requirements. So requirement one, we need a valid random sample, which I'm going to go ahead and check off. Anybody that does any kind of work in statistics by now should know that you need a valid random sample. And that allows me to just assume that that is true. Two, do we have independence? This one's a little bit tricky because remember, independence is basically you're asking, is your sample less than or equal to 0.05 of the population? And whenever you're dealing with Americans, we're going to go ahead and check this off. It's safe to assume because there are hundreds of millions of Americans. So this is safe to assume if your population size is large. So the number of Americans, that's a good question as to what it is. It's right now probably 370 million. So we can always look that up on Google. Yeah, let me Google it on my desktop here. Let me just quickly verify. Number of Americans. And I'm not counting citizens. I'm just basically saying Americans, people that live here. The U.S. Census Bureau in 2024 said the U.S. population reached 340 million in 2023. So that was a couple years ago. So 340 million in 2023. So this year, if we project that, I believe it should be around 360. But anyway, all we need to know is it's fairly large. So 5% of 340 million, that's I think like 30 or is it 30? It's some 100,000 number of people. So my sample size is for sure less than, like 100,000 individuals. So 5%, just to be safe, we can say is, about 100,000. You got to actually compute it, but you'll see it's still several hundred thousand individuals. So for sure, my 1,000 individuals is less than that. All right, now comes the last part, part three, which usually is one of the only ones that you really need to put in work. Three, do we have the shape requirement met? So in other words, do you know that the random variable of interest, which in this case is the number of hours that Americans are working, is that normal? And usually it's given to you here. They did not give it to me. Or you need to make sure that you have a sample size that's large enough, which for us is n greater than or equal to 30. So for this example, I do not know that the random variable, which is the number of hours worked, is actually normal. So we need to go ahead and ask the second one. Is my sample size bigger than 30? And the answer there is yes. All right, so we've satisfied all the three requirements. That means that we can now go ahead and construct the 95%, sorry, not 95, 99. So now they're saying go ahead and create a 99% confidence interval for the true mean number of hours worked. You can do this by hand. Let's just emphasize. You just got to find T sub alpha over 2. So if you were doing this by hand, you would need to go ahead and find what is T sub alpha. So you'd make your sketch. You want a 99% confidence interval. And so if 99% is in there, that means that alpha is 1%. And 1% is 0.01. Then in the tail, you have half of that. So alpha over 2 in this case would be 0.005. And you can go ahead and find T sub alpha over 2 using a table or technology. The degrees of freedom for this, by the way, are very large. So my sample size is 1,100. So if I subtract 1, my degrees of freedom in that case is 1,099. So let's go ahead and actually find this by hand. So I'll go to stats, calculate. Remember that anytime you have a distribution and you're trying to find a probability or value, you go to calculator and you select your distribution. In this case, I pick T, and I'm going to go ahead and type in my degrees of freedom, which is 1,099. The area to the right has to be 0.005. And notice that I have a picture that's very much the same as what I sketched earlier. So In this case, my critical value is 2.5803. All right, and now we have everything that we need to do this by hand. Now we just simply substitute. We know this value now, T sub alpha over 2. We know the values in green, S and X bar. And adding it and subtracting will give you your answer. Notice that if we use StatCrunch, we're using a T distribution, and that means that I would need to go to stats, because I'm creating statistics, and now I go to T-stats. We have a single sample, and I have a summary. So my sample mean was the mean number of hours worked. So let's just go back and revisit that. It's right here, 43.6. S standard deviation, 15.23. And sample size was 1100. So let's type all of that information in. So sample mean was 43.6. Standard deviation was 15.23. And my sample size was 1100. I'm going to change this to confidence interval from mu and then adjust the level. So I believe this was 99% confidence level. Yeah. And I can press compute. All right, and there we go. We have a summary now. Notice degrees of freedom is here, and my output is 42.4 and 44.78. Remember that if you want to rate the critical value, you can go ahead and select this option here, show critical value. And now you have the critical value posted here. So I have a printout of this result in our notes, and we can verify that we have T sub alpha over 2 is the same that StatCrunch reports. And we have our answer. So my answer here is going to be the lower bound and the upper bound. So my confidence interval is 42, 42. Sorry, that should be 42.42 hours and 44.78 hours. So my interpretation here is going to be that we are 99% confident. That's very important. That the true, and then go ahead and tell me what it is that you were making a claim on. We have the information right here. We were trying to make a claim regarding mu. So it's the true population mean, number of hours worked, last week. I guess I should emphasize that this is only for Americans, right? Because that's where my sample was. So this should only be Americans, not necessarily, you can think of maybe French individuals. This is only for Americans or Indian individuals in that country. So we are 99% confident that the true population mean number of hours worked last week is between 42.42 and 44.78 hours. So right now you're saying, I don't know where the true mean is, but it's got to be between 42.4 hours and 44.7 hours. That means that if a company, for example, reports that the average number of hours worked is 40, we do not agree with that. Right? So I'm trying to answer this question. If a research firm reported the average number of hours worked is 40, I disagree, because according to my sample is saying that the true center is much higher. It's between 42.4 and 44.78. Remember that this claim is based on the idea that we understand how samples behave. So if I understand how sample means behave, I know that the sample mean will be close to the population mean, that's why I can go ahead and say this, that getting a sample that lands very much off to the right-hand side, right, if I get a sample that lands over here, and then I can go ahead and add the variability, then I'm saying whatever this lower limit is and this upper limit is, they will be fairly close to this true center, which is the population center. So I like this picture here because we actually do miss 40. So if they're claiming that the center is 40, we're like, no, it's not, because I understand that the sampling distribution of the mean means that my samples will be close to the mean, which you can see here is actually further to the right-hand side. So that is how everything is coming together. And I hope that this example makes sense. We're going to see another example that's a little bit different in the next video that will require a lot more work. So please watch this. If any of you have any questions, make sure you reach out, and I'll see you in the next video.